Hey there everybody, this is another video for my 30SH Pre-Cal Honor students, and we are in the second part of lesson 2.3 in the Trigonometry Part 3 T3 outcome, and this is the ambiguous case of the sine law. And very often I'll start this lesson with asking students if they know what the word ambiguous means. It's not a math term, it's a term that actually has kind of meaning in everyday language, but it's not a word that you hear used very often. So I get guesses from students like, does it mean that you're just as good with your left and your right hand? And it's like, no, that's ambidextrous. Does it mean that you're a real go-getter and you want to succeed in business? It's like, no, that's ambitious. Ambiguous actually means uncertain, unclear. It means that the situation could go one or more possible ways. We don't know which way it's going to go. So the ambiguous case of sine law, and I love that title, the ambiguous case of sine law. It sounds like an Agatha Christie novel. When solving a triangle, you are given the measures of two sides and an angle adjacent to one of those sides, also known as side-side angle. Whoever wrote these notes is a wimp. I call it angle side-side. We're grown-ups here. That's not going to make us giggle. And when you see angle side-side, there are four possibilities. The four possibilities are, number one, no triangles exist. No triangle could have those measures. Possibility number two, one triangle exists that has the given measures, and there is a right triangle. Oh, I forgot the T. Right triangle solution. I don't know why that blank's not longer. Possibility number three is one triangle exists that has the given measures, and there is an obtuse triangle solution. And then number four, two triangles could exist that have the given measures, and there are two possible solutions. When there are two solutions, this is called the ambiguous case. So the ambiguous case occurs in a angle side-side triangle where the given acute angle is the opposite to one of the two given sides, and where that opposite side is both longer than the adjacent side but long enough to form a triangle. That sounds really complicated. It's actually very easy to understand if we draw a few pictures. We did a little activity in class that you might have done before you see these notes. Some of you will do the activity probably after you see these notes. And whichever your case is, let's just all pause for a minute and enjoy the space. Isn't that a nice space? Isn't that just a beautiful? Let's just all enjoy the space. Space. What I'm saying is I have no idea why there's all this space here, because we can actually flip to the next page and start the notes here again. Given a angle side-side problem, there are four possible scenarios, kind of like Goldilocks and the four bears. Yes, I'm right. It's Goldilocks and the four bears. No, it's not the three bears. You're just not remembering the story right. I think you were reading from a faulty book. So here is the situation. First of all, we could have a situation where we have angle A. We'll put angle A down at this corner, very similar to that activity we did, or that you're going to do. Angle A is 30 degrees, and this is side B, which is going to be, say, 6 units, could be centimeters or whatever. And the side across from angle A, which also is going to be side A, remember you always label angles and sides across from each other with the same letters, is only 2 units long. So think about it. If this line here is 6, about a third of that would only take you down to here. So side A would be 2 centimeters. And as you can see, that's not long enough to join down. It's like, well, can I bend this up? No, then you'd lose the 30-degree angle. So it's just plain old too short. That doesn't work. That's no solution possible. So that's case one. Case number two is that you get exactly a right triangle. So you have angle A, which again is going to be 30 degrees. And again, this is going to be 6 units. But now this is going to be 3 units, and that exactly just makes a right triangle. Now, how do I know that? Well, you should probably remember from your unit circle that the sine of 30 is in fact a half. So that means that if this is 3, that has to be 6. The proportion has to be 3 over 6, which is 1 over 2. That's the way sine of 30 works. But think about it. If this line here was even just slightly shorter than 3, like if it was 2, obviously it doesn't make it. But even if it was 2.5, it would only make it, to there. What if it was 2.7 or 2.9 or 2.99 or 2.999? If it isn't at least exactly 3, it isn't just right, and it's not long enough to make this triangle. Think about it the other way too. What if this 30-degree angle were just slightly bigger? What if it was 31 degrees? Let's use our calculator. Think about this. The sine of 31 degrees times 6 would be just too big to be 3. So if this was 31 degrees and that was 3, it still wouldn't reach. So basically, if you want to know if you have a situation where the line either is too short or just right, you can actually kind of use this little formula. The sine of angle A times the B side has to be less than or equal to the A side. So when I have the sine of 30 times 6, and I get 3, well, 3 is exactly equal to 3, so it works. If I had that, instead of this being a side, say I had, instead of a side that's 3, I had a side that's 4. Well, that would go this way, and it wouldn't make a right angle, but would totally make a triangle. So the sine of 30 times 6 would be 3. 3 is less than or equal to 4. Check, that would actually make a triangle. So a triangle is only possible if you meet this criteria given angle side side. If angle side side is such that this is an equal, it's a right triangle. If angle side side is such that this is more than that, you're too short. So keep that in mind. And let's move on to the ambiguous case. That was what we came here for. That's what we paid our admission for. Let's look at it. The ambiguous case happens when, for example, I make, again, a good old 30-degree angle. And this side is going to be 6 again. We just seem to like those same numbers over and over again. But this time, side A is 4. And side A is 4 can go two ways. It can go this way, kind of make a long, skinny triangle. Or it can go this way. And make kind of an obtuse triangle. And if you're looking at this and going, well, wait a minute, like, you don't get to just make that side as long as you want. Actually, I do, because if this is A, and this is A, and this is A, and this is A, and this is 6, which is, of course, side B, and this is 6, which is, of course, side B. Notice it doesn't tell us, I'm going to make that 4 equals A, or how about I write it as A equals 4? That's bugging me. That looks stupid. There we go. Notice it doesn't say anything in these givens about how big angle C has to be. Or sorry, angle B has to be. It could be obtuse. It could be acute. I don't know. I don't know anything about angle C. It could be acute. It could be obtuse. I don't know. I don't know anything about how long side C is. So they could be anything. If those are my only 3 givens and the situation is that the opposite side is shorter than the adjacent side, but long enough to make a triangle, and not a right triangle like that one, then I have an ambiguous situation. I really don't know which of these 2 triangles it is. It's ambiguous. If, however, this side, this opposite side, is longer than the adjacent side, it's too long to be ambiguous. It still makes a triangle. So it's 30 degrees. And this is, again, B is equal to 6. This is angle A. But if side A is longer than 6, like, for example, it's 10, well, notice I couldn't put a 10 line this way. I'd go past this base, and I can't because I have to make that a 30-degree angle. That's a given that it's 30 degrees. So the only way I can make this is to make a very long, obtuse triangle. I might have exaggerated that just a tad, but you get the idea. A would be 10, and that'd be my only option. The only solution possible is this big obtuse triangle. So how can you tell whether you have this or this? Well, once again, this line, this opposite to the angle I'm given angle side side. See why I like calling it angle side side first? Because I start by thinking about the angle side side. The second side, the one that's opposite the angle, is shorter than the adjacent side. It's still long enough that it's not a right triangle or no triangle, but it's not long enough to escape this possibility that we have two separate triangles. So let's keep that in mind as we do some example-y. And let's see, I think we actually only have like, do we have one example for this? Is that all we have? Really? We only have one example? What? Am I right about this? 22, 23, yeah, you're right. Okay, we only have one example. Well, we better make it a good one. So let's see, the example is, in triangle ABC, A is 12, B is 18, and A is 36 degrees. So I have a 36 degree angle here at A. I have side B is 18 degrees. And I have side A that's across is 12. Is 12 big enough to even make a triangle? Well, let's see. Is the sine of 36 times 18 less than 12? It is. So it's going to make a triangle, but it's going to make two triangles. It's going to make a triangle here, like that, where that's A equals 12. And it's going to make a triangle where I'm trying to make this the same like angle as that. I don't know if I'm succeeding. And this time, instead of the 12 heading that way, the 12 is going to head this way. And now, guess what I get to do? I get to solve them both, because they're both valid answers. And when it says solve the triangle, hopefully you remember this from grade 10, solving the triangle means find all missing sides and angles. So I'm going to do this in two parts. I'm going to call this angle B. I'm going to call this angle C, which means this is side C. Okay, that's side B. I'm going to call this angle B primed. That's like a little exponent of 1. It's actually kind of like more of an apostrophe. So B primed, this is going to be little c primed, and this is going to be angle... No, hang on a sec. Sorry, this is B. What am I doing? Sorry. Can I have a mulligan on that? I called this side C at the top. This has to be side angle C primed. Sorry. Angle B primed is over here. So let's start by using our sine law. The sine law says that I have, if I'm going to solve this thing, I need a side across from an angle, and I've got that. I've got this angle across from this side. So I also have this angle and that side. So I'm going to solve for angle B. So the sine of angle B over B is equal to the sine of angle A over A. So cross multiply, sine of angle B is equal to B times the sine of angle A over A. Okay, now I plug in numbers. The sine of angle B is equal to little b, which is 18, times the sine of angle A, which is the sine of 36, over A is 12. Now, will my calculator know that this is an ambiguous situation and spit out two different answers? It most certainly will not. I'll use this calculator for a change. So 18 times the sine of 36 divided by 12. Boom, 0.88. So the sine of angle B is decimal 88 something. So angle B is the inverse sine of that, inverse sine of my answer. And I get 61.8 degrees. So clearly 61.8 and change. That doesn't quite look like 6 degrees. It looks kind of obtuse, but you get the idea. Actually, you know what? Now that I think about it, it's kind of given me this answer, hasn't it? It's given me the acute answer, and that's actually the way that the calculator is going to do things. The calculator is going to give you the acute answer. It kind of, as a default setting, gives me an acute angle. So you might be thinking, well, then how do I figure out the obtuse angle? How would I figure out this one? Well, if this one is 61.8, I want you to kind of imagine if I could put these two diagrams together. If I could like overlap them. In other words, see this line that instead of swinging out that way, I swung it in that way? What if I swung it in this way right here? So think about this. This we just figured out is 61.8 degrees. Cover that up. What do you notice about that triangle? What do you notice about my hands other than the, my fingernails are dirty and I have like, I've injured myself here. What do you notice about that triangle? Well, that's 12. That's the same line but in the other direction. That's 12. Hey, that's an isosceles triangle, which means this angle in here, this sort of imaginary angle, would also be 61.8 degrees, which means that this angle here and the 61.8 add up to 180. Ooh, there's a word for that in geometry. When two angles add up to 180 degrees, we call those angles supplementary. So angle B here in the obtuse side of the triangle, angle B is going to equal to 180 degrees minus angle B prime. So that's going to be 180 minus the 61.8 degrees. So I'll take my 180 minus that answer, and there it is, 118 point, I'll just round it to one place, 2 degrees. So there's my two answers for angle B. Now, if I have two answers for angle B, I have to have two answers for angle C. So let's go to the acute triangle first. Now remember, this stuff here I just kind of added in to think about how big this angle has to be. So I'll just get rid of it again. Don't want to dirty up my lovely picture here. So what do I know about angle C primed? Well, angle C primed would be 180 minus 36 plus 61.8. And you know me, I don't like losing accuracy, so I'm going to actually go 180 minus that answer again. There's that 61.8. And now I'm going to go 180 minus, open a bracket, 36 plus that answer. And angle C in this diagram, C primed I called it, is 82.2 degrees. So there's that one. Now what about the other angle C? Can I do that same trick? Can I just find the 180 minus that? I don't know. What do you think? Will that work? I kind of doubt it. I think for angle C in this one, I actually have to go back to what angle B was and say that this angle B plus 36 has to subtract from 180 also to get angle C. So angle C is 180 minus 36 plus 118.2. And let's see if we get that right. Let's see. So, how do I get that number back? Oh, I wish I'd have saved that number. Rats. Okay, you know what? I'm just going to get that number back. I'm going to go 18 times the sine of 36 divided by 12 inverse sine. My answer is, there it is, 61.8. So, 180 minus, oh wait, I want the 118.12 this time. Ha ha ha, whoops. So 180 minus the answer. There we go. That's the one number I want. So I want 180 minus 36 plus that number. So 180 minus, open a bracket, 36 plus my answer. Doo-doo-doo. And it makes sense when you look at the way the picture looks that in the ambiguous case, you're usually going to get one really skinny angle up here, which makes sense, right? Because remember that angle had to cut in that way, so it makes a very skinny one up there. Oh, I'm pointing up here and you're not looking. Up here is a very skinny angle, which is what I got, a very skinny angle. So that makes sense. And okay, what do I need? I've found the two angle B's, I found the two angle C's. Oh, I need two side C's. Okay, let's kind of ponder this for a sec. This side C is in a great big kind of, or in an acute situation, it's a longer side. This one's going to be kind of much smaller. So I'm expecting C to be smaller than C primed. Now that I know angle C, I can find both of them. So I'll find angle C over, let's see, this is the one I just found, so I'll do this one. Angle C over the sine of angle C. So side C over the sine of angle C is, and I was given A and A. So that's going to be, so let's see, A was 12. So A over the sine of A. So C is equal to A times the sine of C over the sine of A. Plug in my numbers. So my number for A was 12. The sine of angle C is the sine of this angle I just found, 25.8 degrees, divided by the sine of, we were given 36. So side C is 12 times the sine of the angle I just found, divided by the sine of 36. Boom! 8.9 and a bunch of change. So I'll round it to 8.9. And what are we in here? Centimeters? It doesn't tell us. Units. Good enough. If it doesn't give a unit, I don't need a unit. And that's one more thing to find. What if that'd be this kind of short C here? What about this longer C primed here in this triangle? Well, for that one, I'm going to use the exact same formula. You know what? I'm just going to copy it again, but I'm going to use I'm going to use C primed is equal to A times the sine of C primed over the sine of angle A. And that's going to be, okay, so A again was A was 12. Oh, we froze. There we go. A was 12 times the sine of C primed, and C primed was 82.2 degrees. Ugh, I don't actually have that number. I can't. I'll use a rounded number. Ooh, I feel unclean having to use a rounded number. And divided by the sine of A. What was angle A again? 36 degrees. And there we go. So that's going to be 12 times the sine of 82.2. If I really did care about accuracy, I would have stored some of these numbers into my memories in here so that I could access them without rounding them. And divided by the sine of 36. That's going to be close enough. It's going to be 20.2. And we did predict that this would be much longer than that, which it is. So I can finish off the triangles. They are now solved. This C is, what was it, 8.9? This C primed is 20.2. And this angle C up here, we found that was the little skinny angle of 25.8 degrees. And there you go. The two triangles are solved. Oh, I forgot to put angle B in there. What was angle B again? B was 118.2. And this angle B I already wrote in. So there we go. I now know all three sides and all three angles in both of these triangles, which come from those givens. That's the ambiguous case. Sometimes you gotta solve twice. Cool. Try some of the ones that we're gonna assign in the homework and have fun.